Okay, you finally made it to the last unit of AP Calculus. We're going to start our Unit 9 here with the idea of parametric equations. And if you have no idea what a parametric equation is, don't worry, you're not alone. But what I want to show you here now is we're going to mess things up. And instead of having an equation of y equals to x, like that, now what I want you to understand is with a parametric equation, both the x value and the y value are dependent. And they are dependent on another value, on an independent value. And what would we actually use to represent the independent variable in this case? It's not x anymore, usually t. Okay? So think of now both x and y depending upon the value of t, and t usually represents time. So let's take a look at example number 1, where I'm going to ask you to plot these points to actually sketch the curve. Notice my graph here is both x and y, but notice my x value is based on the function of t, similarly with y, and I've given you the t values that I'd like you to try, -3 all the way to 2. So if you're doing it this way, your goal is to find the x and y coordinates. So I'll plug in -3 for t, so that's -3 squared is 9, 9 minus 5 is 4. Do the same thing with the y value, you get -3 over 2, so I'll plot that point first, 4 comma -3 over 2. Here is the value when t equals -3. We'll do the same thing with -2, so -2 squared is 4, 4 minus 5 is -1, that's -1. So here we go, this is where t equals to -2. We'll do the same thing for -1, and I think you get the idea now, right? I hope you do. So this is -4.5. So notice the graph seems to be going like this. Be nice if I actually connect the dots together, right? And then at 0, we got -5 for x and 0 for y. So it comes here. Notice the direction then that I'm traveling as t increases. When x equals to 1, that's -4.5. And I believe this is -1, -1. So back up to here, and then up to here. So notice what I'm drawing here now. There you go. So here is a plot of the parametric equations given by x equals to t squared minus 5 and y equals to t over 2 for the values of t between -3 and 2. Now I arbitrarily gave you this. I could have said t goes on forever and ever, and you'd have to continue drawing the points. Okay? So that's one way of plotting the curves, but maybe that's not the best way. Another way of doing it is to actually change the following parametric equations back to what I call rectangular form. So the rectangular form is what we're used to, y equals f of x. Okay, and the idea here is you need to eliminate the parameter. The parameter in question is our independent variable, so we have to eliminate t. So I'm going to try to use this equation for x. I have a square root, so I'm probably going to square things first. That I think helps me out, because now it shouldn't be that hard to eliminate t. I'll just do the reciprocal on both sides, and notice now t equals to 1 over x squared plus 1. Oops, I mean minus 1. Noting this, I can then substitute this into the y equation, so 1 over x squared minus 1, all over 1 over x squared minus 1 plus 1. That gives me 1 over x squared minus 1 on the top, or the numerator, and 1 over x squared on the denominator. Probably one of common denominator things in the top, so x squared 1 minus x squared divided by 1 over x squared equals to y. And since the denominators are the same, we can divide them out, and you're left with 1 minus x squared. Now notice I had a restriction here that t had to be bigger than -1. So understanding that, if I plug it into my x equation, notice here then, I hope you can see that the x value can't be negative as a restriction. and so therefore x has to be bigger than 0. Okay, so notice x can't be negative with the square root there. And so now if I ask you to graph this, hey, y equals 1 minus x squared with x is bigger than 0, well, that's just a parabola, so that's great. A parabola that starts at 1, goes downwards like this, with an open dot. Okay? Now the last thing you need to look for is, you know how on the previous graph I had these arrows here to show the direction? So I want to do the same thing here. I know this arrow just means that I'm extending the graph down forever and ever, but it doesn't represent the direction of how this graph is created. And in order for us to look at the direction, then you have to think what happens when t is greater than -1, and think about making that chart again and saying, hey, when t equals -1, what happens, then 0, what happens, then 1, what happens, and so on. Okay? Noticing here, if you think about this, looking at the y equation, when the t value gets bigger and bigger, it seems to approach the value of, yes, we're doing limits, of 1, and so it looks like to me that the graph goes from low like this to the high, and so the direction of travel looks this way. Okay, and there's your sketch of the graph. Alright, moving on, more eliminating parameters. This time the parameter we don't use is t, but it's theta. Nonetheless, same idea. Okay, so theta is our independent variable in this case. We want theta to be between 0 and 2 pi. So let's see if we can sketch out what this looks like. Now, in this particular example, you could do the same thing before and try to isolate the parameter. So isolating the parameter of cos would give us inverse cos x. That's not a good idea. Yikes. I hope you remember your trig stuff, because there's one special Pythagorean identity we'd like to use here that will help us out, involving cosine and sine. Do you remember sine squared theta plus cos squared theta equals to 1? Remember that? Well, why is this going to help us out? Well, because if I want to solve for sine theta, what I've just told you is that sine theta is y over 3, so sine squared theta is just y over 3 all squared. And since you already have here cos theta, that's equal to x, so that's great, that's x squared. And that equals to 1. And if I rewrite this, this is x squared plus y squared over 9, and that equals to 1. This is sort of like a circle. It's actually a circle with vertical expansion. Remember? Vertical expansion by a factor of 3. So what is this thing called a circle with a vertical expansion by a factor of 3? Well, if you think about it, what that means is that the circle with radius 1 got expanded to 3 vertically, but the radius is still 1 horizontally, and so you don't actually get a circle, but you get the lovely, yes, ellipse. Okay. Now, I've shown you 3 examples of parametric equations and how we can draw them out. No calculus involved until now, because even though equations are given in terms of a parameter, it is possible to find dy dx and d squared y dx squared, so the first derivative and the second derivative, by differentiating and then dividing. So if you want to think about it, I've told you here in the box, and once again these are formulas you should memorize and put on your formula sheet, but think about it this way. Think of the dy dt as the vertical velocity. Of the particle. And dx dt would be the horizontal velocity. And so dy dx is really just the slope of the tangent of the ratios of these two velocities, right? So the slope of tangent is just the ratio of the two velocities. So therefore dy dx is just equal to dy dt divided by dx dt. Okay. Now, how do we get d squared y dx squared? That's the second derivative. Well, to find the second derivative over here, all I want you to do is, the idea is just, let's replace, the y in dy dx with another dy dx. So, here we have d squared y dx squared. And instead of having dy dt, it's now d dt. And like I said, replace the y with, so I'm replacing this y right now here, that particular y, with dy dx. And I still have a dx dt in the denominator. And that's how you get the actual formula there. Alright? So, memorize these. We're going to use them. Next page. Alright, so unfortunately for me, they're on two different pages. So what I'm going to do is rewrite the actual formulas here. And this will be a good way for us to memorize them anyways. So dy dx is equal parametrically to dy dt over dx dt. The second derivative of d squared y over dx squared is equal to d dt of just dy dt divided by dx dt. Alright, let's use them then. So, if we've got example number 4, where x equals to cos t and y equals 3 sine t, let's find dy dx, which means I should find the individual velocities or derivatives first. The derivative of dx, or of x, is dx dt. Derivative of cosine must be, you got it, negative something. And therefore also I'll find dy dt now. 3 sine t must be 3 cos t. And so therefore if I want to find dy dx, it's just the ratio of these things. So 3 cos t divided by negative sine t. And hopefully you remember trig very well, because cos over sine is just, you got it, negative 3 cotangent of t. And that's dy dx. Okay, now trying to find d squared y dx squared using the formula that's ddt of dy dt, the derivative of dy dt. Here's dy dt. So the derivative of cos, well, the 3 is there. The derivative of cos is, oh, wait a minute. Did I say dy dt? Oh, I made a mistake. It's not dy dt, it's dy dx. Ah! Oopsies. Remember, you're supposed to replace y with dy dx. Oops, oops, oops. Make the change. My fault, my fault. Oops, 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 oops. So, back to here. D squared y over dx squared is ddt of dy dx. So I need the derivative with respect to t of the derivative. So I should be looking here. So negative 3 is a constant. Now what's the derivative of cotangent? I hope you remember this is cosecant squared. And then dx dt we found earlier, that's just negative sine t. Negative, negative, a whole bunch of negatives, still becomes negative 3. And here we have here cosecant squared t over sine t. Sine, I hope you remember, 1 over sine t is the same thing as cosecant t. So we can rewrite this as just negative 3 cosecant cubed t. And that's our final answer. Okay. We can use this stuff again to think about slopes on concavities. Remember, concave up means the second derivative is positive, concave down, second derivative is negative. So I'm going to leave this as an exercise for you now to try. And even number 6, I think below, you can probably try this. It's just a review, writing an equation of a tangent line. Remember, y equals mx plus b. So you got to find out the slope and all that kind of stuff. So I'm going to leave these two for you to do. Okay, so follow the same steps as before for number 4, and you should be on your way. Don't cheat, okay? So actually try these yourself first, and then come and check your answers with me. See you soon. I want to find the slope at the point 2, 3, so I'm going to plug in the values of 2, 3. But you're like, wait, I have t as my variable. You're right. So when x equals to 2 or y equals to 3, what is the value of t? So you plug it back into the x equation. 2 equals root t, you'll see that t equals to 4. You can get the same answer by plugging in 3 equals to y. You should still get t equals to 4. So the slope in this case is really dy dx evaluated when t equals to 4. That's nice because now I can use the actual equation here, and I see it's just 4 to the power of 3 halves. That's just it. D squared y dx squared is the derivative of dy dx with regards to t. So ddt of, in this case, t to the power of 3 over 2 divided by dx dt. That derivative is 3 halves t to the 1 half. Dx dt is once again 1 half. T to the negative 1 half. 3 halves divided by 1 half is 3. T to the power of half minus t to the negative half is adding a half plus a half, which is just 1. And once again, if I want dy dx squared at the point 2, 3, that's equivalent to me using the derivative or the second derivative at t equals to 4, plugging that into our expression. 3 times 4 must be 12. Since 12 is positive, we know the curve is concaving at 2, 3. Ta-da! Okay, example number 6. Tangent line, tangent line. I probably need the stove. Notice you also need an equation at a particular point. The point in time here is t equals to 1. And so if I want a point that's actually on the Cartesian coordinate, I better plug in t equals to 1 for x. So x equals 0. Y equals to 2. So this actually transforms into the point 0, 2. Here's your point. And so now let's go ahead and find dy dx. Dx dt just equals to 1. Dy dt, what's t? Negative 1. Negative 1 over t squared. Plugging in at 1, you'll see that I get, well, dy dx equals to dy dt over 1. Or in this case, just negative 1 over 1 squared, or negative 1. Great. So I've got my slope, negative 1x plus b. I've got my point over here, so let's plug it in and solve for b. b equals to 2. So my equation is y equals negative 1x plus 2. Did you get that? If you did, I'm grateful because you got it right. Okay, one last application here, and then we'll be done for today. Arc length. So, once again, you've seen arc length before, haven't you? Before we had a formula for arc length, do you remember? From the previous unit, I think chapter 6, was it? Remember arc length? Do you remember it? Say yes. It makes me feel better. Remember this? dy dx all squared times dx. I think it was a supplemental sheet I proved it to you. Well, the question is, how do I get the arc length for a parametric equation? Gave you the answer, but where did this come from? So let me quickly try to prove this to you. Well, what's dy dx in our situation here? Well, that's the same thing as 1 plus, and dy dx, we told you earlier, was, right over here, dy dt over dx dt. I can write like this: dy dt. Just trying to save some room. Dx dt all squared. Now I'm going to rewrite this dx also as dx dt times dt. Okay, dt dt's cancel and still dx. Okay, how do I simplify this now? Since it's a square, I guess I can rewrite the 1 as dx dt over dx dt squared plus dy dt over dx dt all squared. Still have that square root on top of everything. Whoop. And I still have the extra dx dt times dt. Okay, so I just changed the 1, made that 1. Notice now both the denominators here are dx dt all squared. So I'm going to take that out and take it out of the square root sign to give me just 1 over dx dt. And what you have left over inside is just the dx dt all squared plus the dy dt all squared. And you've got the dx dt with this dt. And I hope you can see goodbye, goodbye, and you're left with our lovely formula here. Okay, so the arc length of the parametric, you're going to go from a to b, but it's the square root of dx dt all squared plus dy dt all squared, to square root of that whole thing with a dt at the end. Okay, curve though must be smooth and not intersect itself. So using example number 6, I'm going to ask you to find the arc length on the interval from 1 to 3. So using the formula, arc length, interval goes from 1 to 3. Dx dt I calculated already for you is 1. Dy dt I calculated that for you is negative 1 over t squared, all squared, dt. And that equals to the integral of 1 to 3. 1 plus 1 over t to the power of 4 dt. I have no idea how to integrate this, algebraically though. So guess what? Yes, 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 yes. It's time to use your graphing calculator and use it to help you out. So, the square root of 1 plus 1 divided by t or whatever, x to the power of 4, comma x, comma 1, comma 3. I think I forgot a bracket, did I not? I think I forgot more than the bracket. Close the bracket, comma, there we go. 2.1466, remember 3 decimal places on the AP exam, so how about 2.147 units long. Okay, that's it for parametrics. I hope you understood this, because you're going to need it for next day. Next day stuff gets a little bit more tricky, just a little. See you then.